Hello everyone, welcome back. This is Soumya Reddy S, currently studying in Sri Venkateshwara College of Engineering from the Department of CSC, wearing the USN 1VE 21CS067. Today I am here to discuss about the quicksort and its time complexity from the subject of design and analysis of algorithm. The contents are Introduction to Quicksort, how Quicksort works, Quicksort algorithm, the complexity analysis of Quicksort, how to solve problem using Quicksort, advantages and disadvantages of Quicksort, and the conclusion. Let's see Introduction to Quicksort. Quicksort is a widely used sorting algorithm known for its efficiency and versatility, and it follows the divide and conquer rule. Quicksort was developed by British computer scientist known as Tony Hoare in 1959 and has since become one of the most commonly implemented sorting algorithms. The basic idea behind quicksort is to select a pivot element from the array and partition the other elements into two subarrays according to whether they are less than or greater than the pivot. The process is repeatedly recursively on the subarrays until the entire array is sorted. The working of quicksort or partitioning, choose a pivot, recursion and combine. First let's see partitioning. Rearrange the elements of the array so that all elements smaller than the pivot are placed before it and all elements greater than the pivot are placed after it. After this partitioning step, the pivot is in its final sorted position and we should choose a pivot. Select an element from the array to be used a pivot. This can be done in various ways such as picking the first, last or middle element, and after that we should do recursion. Recursively apply the above two steps to the subarray on the left side of the pivot and the subarray on the right side of the pivot. Let's combine the recursion. Once the recursion reaches the base case of subarrays with 0 or 1 element, the smaller subarrays are combined to obtain the sorted array. This is the algorithm for quicksort. In quicksort method, we have three steps: pick, divide and combine the arrays. These are shown in this figure. Let's see about the time complexity and analysis of quicksort. The time complexity of quicksort can be analyzed as follows. In the average case, the time complexity of quicksort is 0 of n log n, where n represents the number of elements to be sorted. This average case analysis assumes that the pivot selection is random or uniformly distributed. The partitioning process takes linear time. 0 of n as each element is compared to the pivot exactly once. In the worst case scenario, quicksort can have a time complexity of 0 of n power 2. The worst case occurs when the pivot selection is consistently poor, leading to unbalanced partitions in each recursive step. It's worth noting that quicksort's performance is highly dependent on the choice of the pivot and the initial order of the elements. In the average case, quicksort is efficient and widely used due to its average the time complexity of 0 of n log n. However, in scenario, worst case behavior is a concern or when the input is already partially sorted and the sorting algorithms like merge sort or heap sort may be preferred. Solving a problem using quicksort. Let's go through an example of the quicksort algorithm step by step. Suppose we have the following array of integers that we want to sort in ascending order: 7, 2, 1, 6, 8, 5, 3 and 4. To apply quicksort, we first select pivot element from the array. Let's choose last element 4 as pivot element. Now, next, we partition the array around the pivot by rearranging the elements such that all elements less than the pivot are on the left side and all elements greater than the pivot are on the right side. The partitioning process involves comparing each element to the pivot and swapping them as needed. Now we get 3, 2, 1, 4, 8, 5, 6 and 7. Now the pivot 4 is in its final sorted position. We have divided the array into two subarrays. The elements to the left of pivot 3, 2, 1 and the elements to the right of the pivot 8, 5, 6, 7. When then recursively apply the same process to each subarray, let's focus on the left subarray first. Selecting the pivot element in the left subarray, which is the first element, that is 3. We partition it 1, 2, 3. Now the left subarray is sorted. We repeat the process on the right subarray. Select the pivot element in the right subarray, which is the last element known as 5, 6, 7 and 8. Now the right subarray is now sorted. Finally, we have sorted both subarrays and the entire array is sorted. 1, 2, 3, 4, 5, 6, 7, 8 in the ascending order. This demonstrates how Quicksort recursively divides the array into smaller subarrays, sorts them independently and combines them to obtain the final sorted array. Note that the pivot selection strategy, such as choosing the last element, can affect the performance of the quicksort. Other strategies like choosing the first element, a random element, or the median of 3 can lead to different partitioning and potentially better average case performance. Now let's discuss about the advantages and disadvantages of the quicksort. Advantages of quicksort. Efficiency. Quicksort has excellent average case time complexity of 0 of n log n, making it one of the fastest sorting algorithms in practice. In place sorting. Quicksorts the array in place, meaning it does not require additional memory proportional to the size of the input. Cache efficiency. In Quicksort has good cache efficiency due to its localized and recursive partitioning process, which can lead to better performance in practice. Randomization. By choosing a random pivot or using randomized pivot selection, Quicksort can achieve average case time complexity even for almost sorted or reversed input arrays. Easy implementation. Quicksort has a relatively simple and intuitive implementation, making it easy and implement. Disadvantages of quicksort. In worst case time complexity, in the worst case scenario, when the pivot selection is consistently poor, quicksort can have a time complexity of 0 of n power 2. This occurs when the array is already sorted or contains many duplicate elements. Unstable sorting. Quicksort is an unstable sorting algorithm, meaning it does not guarantee the relative order of equal elements is preserved during the sorting process. Dependency on pivot selection. The choice of the pivot element can significantly affect the performance of quicksort if the pivot is not well selected. It can lead to poor partitioning, which impacts the overall efficiency of the algorithm. Recursive overhead. Quicksort relies on recursion, which can lead to high memory consumption and potential stack overflow issues for very large input arrays. Not adaptive. Quicksort's performance is not adaptive to partially sorted or nearly sorted arrays. It does not take advantage of existing order in the data, unlike some other sorting algorithms like inserting the merge sort. The conclusion. Quicksort, with its efficiency in place sorting and cache efficiency, remains a popular choice for sorting large data sets. While it has a potential worst case time complexity and sensitivity to pivot selection, the algorithm's advantages and practical applications make it a valuable tool in various domains. Understanding the algorithm's strengths, weakness, and performance characteristics allows developers to leverage Quicksort effectively in solving sorting problems. By this, I'll end my session. Thank you.